Hi there, welcome back to another video from the Math Doc. This one is continuing the discussion of inequalities, and specifically compound inequalities, which are sets of inequalities where you have more than just one expression or one inequality, you have two or more. In a previous video, I discussed compound inequalities with an end requirement. Here we'll be talking about compound inequalities with an or requirement. And when we say or, we mean that either one of the inequalities has to hold. So we don't need both of them to hold in order to solve the set. All we need is for at least one to hold. So let's get into it and look at this first demonstration and then at some other examples. So in this top example, we have a compound inequality, again with an or requirement. The first one is x is less than -3. So let's put that on the number line, -3, x is less than -3, or x is larger than 4. Okay, so here's 4, and for any x larger than 4, this inequality holds. Now, since we have an or requirement here, we really are looking for x's that solve either one of them. So we can use this interval here from -3 to infinity to -infinity, or this interval here 4 to +infinity. So we're looking in this case at two intervals, right? -infinity to -4, along with the interval 4, actually this should be 3, -3, so 4 to +infinity. So we're looking to add these in two intervals, and we find that we have two regions where this compound inequality with the or is satisfied. So in this second set of inequalities, we basically have the same numbers, it looks like the same inequalities, but what I did is I flipped the direction of the inequality so that we could look at some slightly different behavior in but a similar or compound inequality. So what do we have here? Let's try to do this in a different color. We have x is larger than -3. So I'm going to just draw this right below the number line so it's not too messy. So we have x is larger than -3, or again, or x is less than 4, right? So here's 4. And I'm showing the intervals that satisfy these two inequalities. So we go from -infinity here to +4, and from -3 here to +infinity. So our solutions are the interval -infinity to 4, and we add that to the second solution, which is -3 to +infinity, and I'm using the union sign here, and if that's foreign to you, just remember I'm just adding up these two intervals. If it isn't, then you know what I'm doing. But basically, we're adding up these two intervals, we're combining them because we have an or inequality, which says we can look at either one of the solutions and they will solve the entire compound inequality. So when we when we add these two intervals together, what we actually get is the entire number line, right? So starting at -infinity all the way to infinity, every x will satisfy either the first inequality or the second one. So this is somewhat different from the first example, because in the first example we did look not for an overlap, but we added the two intervals, but we did have a gap. In this case, they completely they overlap in a certain area, and they completely cover the entire number line. So that is this first example here, and now we'll go on to a slightly more complicated one. So what do we have here? Well, again, we have two inequalities, and they are combined with the OR requirement here. OR. So we know that any x that solves either one of these will satisfy the compound inequality with this OR restriction. So let's start with the inequality on the left. It looks kind of long and complicated, but let's simplify it. So first thing is let's open this parentheses. So we have 2 times x plus 3. Let's open the parentheses. So we have 2x plus 2 times 3 minus 4 is less than x plus 1. Okay, now we like to isolate our variable x, so let's subtract x from both sides, so we will remain with no x's on the right-hand side. So we have 2x plus 2 times 3, that's just 6, minus 4 minus x is less than x plus 1 minus x. Okay, so we have 2x and minus 1x here. So that leaves us with just 1x. And we have 6 minus 4, so that's just 2. X plus 2 is less than. Here we have x and minus x. These cancel, and we're just left with 1. Now, we will move our 2 here to the other side by subtracting 2 from both sides of this inequality. We have x plus 2 minus 2 is less than 1 minus 2. So we have x, the 2 and the minus 2 cancel, is less than negative 1, right? 1 minus 2 is negative 1. So let's find this on the number line. X is less than negative 1 right there, all the way to minus infinity. Okay, now let's look at the second inequality, the one on the right. We have x plus 2 over 2 is larger than 3. Well, our first step will be to multiply both sides of this inequality by 2, because we would like to get rid of this denominator on the left-hand side, right, in order to isolate x. So our goal is always to isolate the variable. Let's multiply by 2. We have x plus 2 over 2 times 2 is larger than 3 times 2. Now, we can reduce these two 2's, right? That's why we multiplied it by 2. We're left with x plus 2 is larger than 6. And now we will subtract 2 from both sides, right? In order to remain with just x on the left-hand side is larger than 6 minus 2 is just 4. So we have x is larger than 4. Let's find that on the number line right there. Okay, so what are our solutions? Well, we have two intervals, right? We have the interval from minus infinity to negative 1, which we combine, right, with the interval 4 to plus infinity. And why do we combine? Again, because we have an OR requirement. So either one has to hold in order for the whole set to hold true. Let's look at just one more example. So we have here our final example for this video. And let's just go ahead and solve it. Again, we have an OR requirement, so either one of these inequalities has to hold in order to satisfy the entire compound inequality set. So on the left-hand side here, we have 5x is less than 4 times x plus 1 minus 3. So let's simplify by opening this parentheses. So 5x is less than 4 times x plus 4 times 1 is just 4 minus 3. Now again, we'd like to isolate our variable x, so let's subtract 4x from both sides so that we only have x's, the variable, on the left-hand side. So we have 5x minus 4x is less than 4x plus 1, right? We have 4 minus 3 minus 4x because we subtracted from both sides. So now these two 4x's cancel. On the left-hand side, we have 5x minus 4x that just leaves us with 1x, and that is less than 1. So we have x is less than 1. Here we go on the number line. Great. So from 1 to minus infinity, we've solved the first inequality. What's up with the second inequality? Well, the second one is pretty simple. It's just x is less than 3. So we'll write that out here, 3. And there we go. So now we see that our solutions do overlap here. What are the solutions? Well, we have minus infinity to 1. That first interval comes from our first inequality here. We unite that, or we combine that with the solutions for x is less than 3, which is minus infinity to 3. Now, since there's an overlap, basically what this equals is just the interval from minus infinity to 3. So in this case, the intervals were somewhat overlapping, and therefore we could basically take just the solution for our second sort of more open requirement of x is just less than 3. So these videos really were focusing on two different kinds of compound inequalities, the AND and the OR. And again, if you want to look up the AND one, the link will be in the description. We will also have a video that compares the two types of inequalities. So again, you can see what the difference is and how they differ, especially when there's no overlap in the solutions of the two different inequalities. So thank you for joining me again. Please subscribe. If you have any comments, I'm happy to hear these. If you have a specific question or an example problem that you're having trouble with, if you load it into the comments, I will take the time to respond and perhaps even upload a video with the solution. So thanks again, and see you in our next video.